I, Dr. Athens Misra, welcome to all of you. And I would like to introduce our noble speaker, Professor Ashish Srivastava, St. Louis University, USA. Sir has received his MSc in Mathematics and MTech in Computer Applications from IIT Delhi. He received Ph.D. from Ohio University under the supervision of Honorable Professor S.K. Jain. Sir is a professor of mathematics at St. Louis University. His research interest includes non-commutative algebra, combinatorics, and mathematical physics. He has published more than 40 research papers in highly recognized journals. He has published two research monographs, one from Oxford University Press and other under London Mathematical Society lecture notes series of Cambridge University Press. His research is partially funded by at Simmons Foundation grant. He is a keen interested in the issues of diversity, equity, and inclusion in universities and human rights of academicians. He is also an active member of American Mathematical Society Committee on Human Rights of Mathematicians. He has supervised three Ph.D. dissertations and have collaborated with 30 different mathematicians from all over the globe. So now I request Sir, please start his talk on an introduction to supersymmetric cluster algebras. Sir,
Thank you. Thank you. All right, so I'm going to speak about supersymmetric cluster algebras. So let me first begin by telling you what cluster algebras are, because these are fairly new things in market. So these were introduced by Sergei Fomin and Andrei Zalowensky in around 2001. And the initial motivation behind cluster algebras was to give algebraic and combinatorial framework for Lustig's work. But now it has a life of its own. It has gone far beyond the initial motivation. It has connections to so many things, especially to physics, in string theory, in statistical physics. In mathematics, it has connections to so many disciplines. For example, number theory, if you have interest in continued fractions, if you're a fan of Ramanujan, as I am, you can see connection of this to continued fractions. Also in knot theory, if you know about Jones polynomials, this is connected to construction of Jones polynomial. It has connections to Poisson geometry, algebraic geometry, representation theory, a lot of things. So what are these? And I've been told that I should not assume too much of mathematical background. So I'll explain everything that I'm saying here. Okay. At some point, I may say something which you'll not be able to understand, but broadly, you should be able to follow things. So cluster algebras are commutative rings with a distinguished set of generators, which we call cluster variables. How are these different from usual algebras? Generally, when you define an algebra, what is an algebra? Algebra means it's a ring which has a vector space structure as well, right? So you know ring, and if it has a vector space structure, then we call it algebra. Now, generally, when one talks of an algebra, you're given generators and you are given complete set of relations at the outset. Right? But these algebras, these cluster algebras are very different. Here what happens is you're given an initial data. It's called initial seed. And as the terminology suggests, the analogy is like this. So when you plant seed, they grow as a tree, right? So same thing here, you are given some initial data, which we call initial seed, which consists of some initial variables and an exchange matrix. And then you are given a combinatorial rule. And I'll get into the details of what those rules are. But think like you are given some seeds and you are given a rule to grow those seeds, okay? And once you follow those rules, whatever grows out of that, that algebra is called cluster algebra. Now, generally, when one talks of algebra, one is just interested in what is the structure of that algebra. Here, the interest is more in the process of growing that algebra, that combinatorial rule, because that gives a beautiful interplay of algebra and combinatorics. So in this talk, instead of focusing on algebra, I'll focus more on the process of getting the algebra, the combinatorial rule, the mutation. Okay. So here is a more precise way of what I was saying. So you are given some variables, say x1 through x of n, and you are given a skew symmetrizable matrix. Now, if you know skew symmetric matrix, you know skew symmetric, right? So ijth entry is negative of ji entry, right? In other words, if you have a matrix A, you say it is skew symmetric if A transpose is negative of A. Right? So skew symmetrizable is a slightly more generalized version. So what does that mean? So we say B is skew symmetrizable if there is a diagonal matrix. So diagonal matrix means you have all the entries zero, only the non-zero entries are on diagonal, right? Where the product turns out to be a skew symmetric matrix. Okay, so in particular, if you just take a skew symmetric matrix, that is a very strong example of skew symmetrizable matrix, right? And then we define this combinatorial rule. So in direction of each variable, we can do some sort of transformation, and we call this mutation. So if I pick the direction of variable x sub k, and I apply this mu sub k, which I'm going to call mutation in the direction of kth variable, right? So the data which was given to me, the set of variables and the matrix, they both get transformed into new data, which is x prime, b prime. Now, what is x prime? You swap the kth variable x sub k for a new variable, which is given by the expression that I have written here. Okay. And the entries of the skew symmetrizable matrix also change. This will be too much of work if I tell you, you can check this is also a skew symmetrizable matrix. And at this point, maybe you are already losing some interest. You're like, oh, how on earth am I going to follow? These are complicated formulas. I have seen it for the first time. It looks unintuitive. How do I figure out what these are? Well, it's not so unintuitive. I'll explain why it is not unintuitive and why it is very easy to understand what these complicated formulas are. It's just that we need to change our viewpoint. So let's change our viewpoint. And instead of talking in terms of a matrix, skew symmetrizable, let me look at the better case, which is a skew symmetric matrix. Now, why is skew symmetric matrix interesting? Because anytime I give you a skew symmetric matrix, you can encode the same data into a directed graph. What is a directed graph? So you know what a graph is, right? You have some dots and you join them by lines. So you have vertices, and when you join two vertices by a line, you call that an arrow, an edge, right? And when you give a sense of direction also, you call it a directed graph, right? So directed graph means a graph which has a sense of direction on arrows, on edges. Algebraists call those directed graphs quivers. So during this talk, when I use the word quiver, you should understand quiver just means a graph where the edges have a direction, there is arrow. Okay. Now, if I give you any skew symmetric matrix, you can always draw a directed graph. Okay. Now, why is that any better? Because now I'm going to translate the scary looking formulas into more beautiful formulas. So the expression now for new variable is, so if I mutate in direction of k, x prime of k is just take the product of all the variables where the arrow is going toward k variable, right? And then plus product of all the variables where the arrow is going from kth variable to this variable, wherever that vertex is, right? And divide by x sub k. Okay? And how do you change the matrix? Remember how we had a complicated expression for exchange matrix? So now since I'm writing in terms of quiver, the quiver changes in the following way. So every time there is a path from xi to xj via this guy xk, we will add another arrow from xi to xj, okay? And we will reverse all the arrows incident on x sub k. And in the process, if there is any oriented two cycle produced, we will delay. What is oriented two cycle? So see if I can go back here. So if you have a okay, will I be able to write now this time? I was able to write last time. Technology is okay. So here, this is an oriented two cycle. So it's a cycle of length 2, right? And it's oriented. So so if anything like that is formed in the process, then we will delete that. Okay, everyone with me so far? And then we consider the ambient field to be the field of rational functions in all the initial variables that we had. And now collect all the variables that one can generate by following all possible sequence of mutations in this way. Okay, and then your cluster algebra is just the algebra that you are going to generate using all these things. Okay. Now, of course, this is the subring of a field, right? Field is commutative, so that means this is a commutative ring. Okay. Here are some interesting examples, and maybe probably if there are undergraduate students and maybe some graduate students probably can understand. So if you cannot understand this, just ignore. The homogeneous coordinate ring of root SI2 that admits a cluster algebra structure. Also the homogeneous coordinate ring of any Grassmannian. So if you take any say n-dimensional vector space and you take the variety of all m-dimensional subspaces, okay, so you get a Grassmann, and in the homogeneous coordinate ring of that also admits cluster algebra structure. But as I said in this talk, I don't want to scare you by talking more about algebra, so I'll again go back to explain the process of getting it. Okay, so if you are still not convinced that what is this mutation business, I don't understand. So let me try to convince you here. So let's take this hexagon. Okay, and let's triangulate it. So what do we mean by triangulation is, let's partition it into triangles. Okay, so there are so many ways in which I can triangulate. So let me pick this triangulation. Right now you can see that this whole hexagon is partitioned into a bunch of triangles, right? 1, 2, 3, 4 triangles. Okay, now what I'm going to do here is So I'll take a vertex for each diagonal that is not on boundary. So this is 1, this is 2, and this is 3, right? These are the 3 diagonals that are not forming boundary, okay? And then between any 2 vertices, I will draw an arrow. And the idea is that if I traverse counterclockwise, if I can move from one to two to the other one directly in counterclockwise, then I'll move. I'll put arrow in that way. So 1 to 2, if I move counterclockwise, I can immediately go from 1 to 2. So this will be my arrow here, right? And 2 to 3, I can go this way, counterclockwise, right? If you take another triangulation, suppose I take this pentagon, right? And I take this triangulation, okay? I have one vertex here, one vertex here. Let me call this 1, this is 2. How will my arrow go? Can I go from 1 to 2 directly counterclockwise? The answer is no. From 1, I will have to go here, right? So I cannot go to 2 directly. So from 2 to 1, yes, counterclockwise, I can come directly here. So the arrow would be this way, right? So, so you take any regular n-gon, okay, and take a triangulation, and then put a vertex for every diagonal that forms triangulation here, except the boundary ones, and then follow this schema of putting arrows. So you get a quiver, okay. Now, if you flip a diagonal here, okay. Now, flipping a diagonal in triangulation means what? Flipping a diagonal means in any quadrilateral, suppose I have this diagonal here, okay. If I say I'm flipping this diagonal, this means in this quadrilateral, I swap this diagonal for this one, okay. And of course, you can see that when we flip the diagonal, you get another triangulation, okay. So here, if I say, so in this pentagon here, if I say flip diagonal containing vertex 1, what does that mean? That means in this quadrilateral here, replace this arrow, replace this diagonal here by this one, okay. Now you can see that this gives another triangulation, right? So if I had replaced this diagonal here by this diagonal, you still get a triangulation. Now this is vertex 1, this is vertex 2, but this time the arrow would be this way, right? Because 1 to 2 you will go counterclockwise. So what does that mean? That means the mutation, the rule on quiver is same what you see when you flip a diagonal in triangulation of an n-gon. Okay, so that is a geometric way to view this. Now, what is the exchange formula that I was writing? Remember the way we replace. So when we mutate x sub k, we get a new variable. We call it x k prime. And how did we get x k prime? We said this is 1 over x sub k, product of all the x sub i's, where the arrow is xi to xk, and product of all the xi. Now, if you want to see what is the most natural prototype of this, again, go back to this situation here. And remember, if you are in a, if you take a quadrilateral inscribed inside a circle, this goes back to high school geometry. Remember these days, people are learning more of computational things than real mathematics. So back in time when people really did mathematics in high school. I don't know if it is taught anymore, but Ptolemy relation is supposed to be taught in high school geometry, which says that if you have a quadrilateral inscribed in a circle, so if you have this quadrilateral, say ABCD, then Ptolemy relation says that the product of the diagonals AC times BD is equal to AB dot CD plus AD dot BC. If you specialize this, you get Pythagorean theorem, right? So at least if you remember Pythagorean theorem is a special case of Ptolemy relation. So Ptolemy relation is exactly what we are doing in the exchange formula, right? So my point is that what looked to you probably like a very abstract, unintuitive formula has a lot of geometric meaning behind it, okay? So, so this is what I was trying to explain. Again, I don't know how many of you are familiar with Teichmüller theory, but what you do on a regular GON, and you do triangle, same thing one can do on any orientable Riemann surface with marked points. One can do triangulation as I have drawn here in pictures. Here you have a triangulation of orientable Riemann surface with some fixed point. And again, there is a notion of what we call lambda length. So one can look at the cusps and one can draw horocycles and look at if you have a geodesic there, it gives a sense of length. And then there is a Ptolemy relation there. So all what I was doing there in the case of triangulation of a regular n-gon, you can do those things in case of Teichmüller theory also. But in any case, if you don't know that, just don't worry. So here, let me work out one, at least one example, so that you get some feeling that you understood at least something in my talk. Right? So here is a very, very simple case of what I'm going to do here. Okay. So let's take two variables, x1, x2, and I draw this river here. So two vertices. There is one arrow. Okay. And if I do all the mutations, so if you do mutation along x1, the data will change from x1, x2. So when you do mutation along x1, x2 remains fixed, right? And x1 gets changed into, when there is no, so empty product is just 1, right? So arrow coming to 1, there is no arrow coming to 1, right? So that product is 1. There is only one arrow going from 1 to 2. So 1 plus x2 divided by x1, right? So that gives us the second data here. And then we do mutation again. So mutation is involutive. If you do mutation along one variable, maybe I can again go back here and explain what I'm saying. So suppose I have x1 here and x2 here, right? When I do mutation along x1, okay, so x2 remains fixed, and the way x1 would change will be 1 over x1. Product of all the arrows going toward x1, there is none, so empty product is 1. Product of all the arrows going away from x1, so that is x2, right? So your new data is 1 plus x2 over x1. Now, if you do a mu1 again on this, right, then it's not too surprising to see that you'll get back same thing, because mu1 square is just 1. It is involutive, right? So there is no point you will do it in the same direction. So then you will change. And so if you keep doing, and then I leave it for you as an exercise, if you keep doing, these are all the variables that you can get. So there are only 5 clusters that you will get, and you will not get any new thing. Okay, so your algebra is just generated by two things that you started with, x1, x2, and three new things that you get in the process. 1 plus x1 over x2, 1 plus x2 over x1, and 1 plus x1 plus x2 divided by x1, x2. These are the only three new things that you get. If you look at the picture, and again, if you remember part of classic geometry, um, if you're familiar with Gauss's pentagram mirificum, which is in Latin phrase for beautiful pentagram. This is the beautiful pentagram of Gauss. I'll get to this later. Uh, Now one can do the same thing on an, okay, how do I get rid of this thing? I don't. Anyway, so I'm not getting into more examples. But here is one very interesting thing that happens. If you look at the example here, remember in the expression, we are dividing by xk, right? So at some point, when you get an expression like 1 plus x1 plus x2 divided by x1, x2, you're going to divide by it, right? And you get a feeling that I'll get a weird rational expression. But look at all the things that you're getting. In the denominator, there is just one monomial, right? You don't have sum of two things, just one term. That's a monomial. So every time you're getting a Laurent polynomial, look at this one. This is even more interesting because at some point, look at x1 plus x3 plus x2, x3 divided by x1, x2. You're going to divide by this, right? And surprisingly, you can look at all the expressions. They're all Laurent polynomials. The denominator is always a monomial. This is the famous Laurent phenomena here, and which says that if you do any number of mutations, you will always end up with a Laurent polynomial. That means in the denominator, just one term, one monomial. Now, this is again something. There is a beautiful mathematics hidden in all these. Let me give you a very, very simple example to illustrate what is happening here. Imagine I give you a recursive sequence. This is something that you can explain to even a high school student. So suppose you start with x1 equals 1, x2 equals 1, x3 equals 1, x4 equals 1. So take first four entries of the sequence 1, and then define rest of the terms recursively as, so x sub n plus 4 is, let's say, x sub n plus 1, x sub n plus 3, plus x sub n plus 2 squared divided by x sub n, right? Now, if you compute the entries of this sequence after 4, so x5 will be 2, x6 will be 3, x7 will be 7, then you'll get 23, then 59, then 314, 1529. Now, look here, when you get 1529, this will be what? This is 5, 6, 7, 8, 9, 10, 11th entry. X11 is 1529. Now, for n equals 11, 1529 would be, so when you are going to compute x sub 15, 1529 would be in denominator. And what is your feeling here? You feel like, okay, I'm going to divide by these big numbers, weird numbers. I mean, 1529 is not such a number where you will think that, oh, things will factor out. And so you get a feeling that maybe I'll start getting non-integer values, right? However, a mystery happens here. And all the entries, so one can prove. So if you meet a high school student and you explain the problem to him, and if the high school student is clever, even using high school mathematics, the student should be able to see that everything is in integers, right? Now, I can give you a very quick proof. This one will require a lot of work, but the proof that I can give is, if you take this quiver then you can actually prove that all the entries of this sequence can be generated by all possible sequence of mutations on the initial seed. Okay, and since we have agreed that Laurent phenomena tells us that at any point it's just a Laurent polynomial dividing by a bunch of ones, one being in denominator doesn't make it a non-integer, right? So that's why it is going to be integer. So okay, how much time do I have? Okay, 30 minutes. So that's Laurent phenomena. Okay, the proof is combinatorial. One takes a special kind of tree, which is called caterpillar tree. It looks like a caterpillar, and then you do induction on the spine of that caterpillar. So now I hope I've been able to convince that these are beautiful structures, algebraic structures, which have some really nice interplay of combinatorics. And it turns out that although what mathematicians did here was same as what people working in string theory had done. So if you're familiar with the Seiberg-Witten duality in string theory, this is exactly what Seiberg-Witten duality does in case of Krüger-Gauss theory, right? So and they call it mutation, so that's why mathematicians also chose the name mutation here. So I'm going to take this notion of cluster algebra, and I want to define a supersymmetric version of it. Okay. So what is the motivation behind supersymmetric cluster algebra? Well, one thing I told you in case of cluster algebra, you don't want oriented two cycles. Okay. Now that's a big restriction in case of a real application in Krüger-Gauss theory. That's quite unrealistic. So one wants to deal with the situation when there are oriented two cycles. So that's one thing, because consider this on-shell diagram representing scattering amplitudes. If you're not too familiar with these terms, here is how you can understand. So when particles collide, imagine you're looking at collider, large hadron collider, right? So particles are inserted into that, things come out. Even when experimental physicist looks at things and does experiment, what happens inside is purely conjectural. Nobody can see because those things are happening at the speed of light. Nobody knows how particles interacted with each other, right? You know what input you gave, you know what output came out. What happened inside the collider, nobody knows. So there is just a mathematical description. You can just theoretically think what happened, right? So scattering amplitude is a way to denote those the data. So you take the helicity and momenta, and these are complicated functions, and generally one represents them using what is called on-shell diagram. Now, if you're getting scared by all those terminology, just think these are planar bipartite graphs. So mathematically speaking, just think like, because the helicity, so there will be some particles spinning upward, there will be some particles spinning downward. So that gives two different kind of helicity, right? So we decide to denote one by black vertex and the other by white vertex, right? So that is bipartite graph, a graph where the vertices are partitioned into two different colors, right? So here you can see a picture of a bipartite graph. Now, I want to associate a Krüger here in a very natural way. So what do? I take a vertex for every face here. So how many faces do I have? 5 faces, right? One is inside and then 4 on the outside, you can see. So I have 5 faces. And then I choose an arrow to have the direction so that it sees the white vertex to the left, right? So so when I go from 5 to 1, it should go 5 to 1 so that it will see the white vertex to the left, right? And so you can see the arrow from 5 to 1 is so between 5 and 1 it is 5 to 1. if you look at 3 and 1, right, it has to be this way so that it will see the white vertex to left, right? And so that's how you are getting these quivers. You can clearly see you have oriented 2 cycles. So you couldn't deal with this in the classical cluster algebra setup. However, in a new setup, which I'm going to define, we will be able to deal with them. And the second thing is the symmetry, because symmetry has always been the central idea in anything in mathematics and physics, right? Whenever there are particles, so why do we care about supersymmetry? Because you know the fundamental particles are of 2 types based on their statistic that they follow. There are some which follow integral scheme, which is the Bose-Einstein statistic, if you're familiar with the great Indian physicist Satyendranath Bose. So Bose-Einstein statistic, those particles that follow those are called bosons. And then there are some which follow Fermi-Dirac statistics. Those are the half integral spin particles. Those are called fermions. So when in any physical phenomena both types of particles interact, then the kind of symmetry that arises there, that is called supersymmetry. And physicists came up with this idea of superalgebras to describe the algebraic property of those supersymmetry. So what is a superalgebra? I told you that um, uh, an algebra is just a ring with a vector space structure, right? So we are going to this super mathematics version of everything. So super vector space is just a vector space that is Z2 graded. So graded by this field of 2 elements, right? 0 and 1. So and then any morphism in this category is going to be those linear maps that preserve grading. So 0 grading ones go to 0 grading, 1 grading one go to 1 grading. And so a super algebra is just an associative algebra where the multiplication map is a morphism in the category of super vector spaces. So now we are going to look at super version of quivers. So we will call them super quivers. So these are quivers where you will have some vertices will be even vertices and some vertices will be odd vertices. So in terms of physics, there are like some vertices which represent bosons, and there are some vertices which represent fermions. Okay, and then the variables can be either mutable. Those are the variables where when you transform them, they will change. And then there may be some which will be frozen in the sense that you cannot do anything to them. They're rigid, they're frozen, right? And here we allow loops between loops on any odd vertex. So loop means, so loop on a vertex means a cycle on a vertex itself, right? That's a loop. So we do not allow loops on even vertices, but we do allow loops on odd vertices. And also, we do not allow oriented 2 cycles between any 2 even vertices, but we do allow oriented 2 cycles between an even vertex and an odd vertex. Okay. And then we put 2 kinds of restrictions. I'm not getting into the technicality of, but let me just say, because okay, I have 20 minutes. So I have some kind of restriction, but those are technical, so I'm not getting into that. Okay. And then we define 2 types of mutations. So mutation of even vertices and mutation of odd vertices. And if you look at the expression, it looks a bit complicated, but there is some kind. So let me just say that there is some kind of rule to change the variables. Okay, I'm not going to explain. It will take too much time. And then there is a rule in which we change the super quiver as well. Okay, which is very much like, so let me briefly say here. So y, so xi I'm writing for even, and yi I'm writing y I or yj I'm writing for odd things. So if you see, if you don't have this part here yi yj, then it is back to what I had said for classical cluster algebra, right? So it is quite similar, but of course, there is new information, so there are some new things here. And same thing here. If you remove the odd things, then it goes back to previous setting. Okay. Now, of course, now we have some new kind of variables, odd variables, the Grassmann variables, right, which anti-commute with each other. So then we have some new rule. Again, this is a very complicated looking expression. So I'm not going to get into that, but there is some kind of rule. Okay, just remember that there is a way to change the odd and even vertices. Okay. It turns out that the even mutation is involutive. The odd mutation is not involutive, but if you do 3 times in the same direction, then it's same as changing it 1 time. Okay. Um, and then as before, we do all sorts of sequence of even mutations, collect all the even vertices, do all sequence of odd mutations, collect all the odd variables that we generate in the process. And then the cluster superalgebra is just the super commutative superalgebra that you can generate it by all these guys. So again, one would want the Laurent phenomena here, because if I don't have Laurent phenomena, then what do I mean by dividing, right? It turns out that you have Laurent phenomena here as well. It requires a lot of effort, so I'm skipping all those things. But with some work, one can prove. If you have interest, you can go to my website, and you can. I have this paper on my website, so you can actually go through the proof. It's a bit complicated, but trust me that there is a Laurent phenomena. Okay, so everything makes sense. Now let me again give you some sort of model to convince you that this is not just abstract nonsense here. Okay, this notion of odd and even mutation. So let's look at the planar on-shell diagram that I had drawn earlier. Okay, and here I explained how do we get a quiver. So remember, we took a vertex for every face, and then we drew arrow in such a way that it sees the white vertex to the left. Okay. Now here, if we do a flip move here means what? I mean by flip that you make the white vertex black and black vertex white. Okay. Physically, what does that mean? That means switching the helicity. So if there was a particle which was rotating upward, it starts rotating downward, right? So if there is a scattering of particles where um, the helicity is switched, it's reversed, then whatever happens to the on-shell diagram and corresponding quiver can be modeled by a sequence of 1 even and 2 odd mutations. Okay, and so that gives you a concrete physical geometric model for even and odd mutations. So my point is that it's not just abstract nonsense that I have just come up with, and I'm trying to sell that to you. there are some physical real things which follow this, right? This is one thing we should always keep in mind, that nature knows more mathematics than us. Nature has better intuition than us, and nature knows more physics than any physicist, right? So best thing is to just observe nature, where you're reading it to. So then there are some natural examples of cluster superalgebras. Anything when you define, you can define whatever you like, but the point is, in order for other people to appreciate that, there should be some natural examples, right? And it turns out that cluster superalgebra, you can find some nice geometric examples. So we have been able to show that there's symplectic orthogonal supergroup, which is denoted by SPO21. Again, it's too much to define all these things. But they admitted cluster superalgebra structure. So you just take my words on it. Okay. Here I have defined what these are. So maybe let me skip this because I have probably 15 minutes. So if you have, again, if you are interested, you can go to my paper and see these things. And also the Grassmannian. So I told you that the homogeneous coordinate ring of any Grassmannian admits cluster algebra structure. So the supersymmetric version of that is, at least in this particular super Grassmannian of 2-0 planes in 4-1, which is the chiral superspace, that one admits kind of cluster superalgebra structure. It is quotient of a cluster superalgebra. Okay. Again, just a quick remark that this is in general the super Grassmannian. So if you ever get a chance to read some work of Yuri Menin, you can see that when you go to super mathematics, a lot of things work out nicely, but then there are some real hurdles. And one of the problems is that super Grassmannian is not always a projective superspace, right? Although this one is a projective supervariety, the one which I'm looking at. So then there is a way to deal with this situation. Again, there's a lot of work, so I'm skipping that. But you can see that so it's a very complicated quiver. But this quiver which I have drawn here, I'm not able to somehow remove this thing. Okay, yeah. So you can see this quiver. This one gives the cluster superalgebra structure. Now, very briefly, I will again mention one more thing, which probably you are familiar with, is the Coxeter-Conway frizz pattern. So what is and what is the connection of this frizz pattern to what I was telling you about Gauss's pentagramma mirificum? Is that if you see this inner pentagon drawn here, right? If you take, so well, it's a bit difficult to follow, but if you take C sub I to be tan square of alpha I, then the Ci follow this formula, okay? And if one takes these, they form this very interesting kind of pattern where if you, so let me maybe write here. So if you have a bunch of numbers here, right, where you have this, that anytime you look at 4 numbers like this, then they satisfy this unimodular rule. Then it is called frizz pattern, right? You can try to write such a sequence of numbers. Let me write one quickly for you, which I have tried to write down here. So if you take a bunch of zeros, right, let's put 1 here, okay, and let me put, so 1 2 1 2 3 3, then I need 5 here, 3 minus 2 1 2, then 1, 4 times 2 is 8, so I need 7 here. So and then you can keep trying. I think by now you have an idea what is happening here. So this is 3 minus 2 I want, so I'll put 1 here. This is 15, so I want 7 here, right, and so on. So you can see if I take 2 times 2 is 4 minus 3 is 1, right? here 3 times 1. So everywhere you will see 3 times 5 is 15 minus 14 is 1, right? So you have this, that is called freeze pattern. So it turns out that they also are related to cluster algebras, okay? And then there is a supersymmetric version, which has deep physical meaning. It relates to Schrodinger equation. But again, we need time to explain those things. So I'm not getting into that, but there is a pattern like this, which I've drawn here, okay? And in some sort of supersymmetric analog of what I was writing. So every elementary diamond satisfies these modified unimodular rules. And it turns out that if you take any generic superfreeze, then the supercommutative superalgebra generated by all the entries of that superfreeze is a subalgebra of a cluster superalgebra. And by taking a quiver like this, somehow I'm not able to get that on the screen. Yeah, here someone gets that, but in any case, that's too much. So I'll stop here. Thank you. So any questions?
Yes, sir. Thanks, sir, for your nice talk, with really beautiful connection among non-commutative algebra, algebraic geometry, and combinatorics. Also, you have explained very well cluster algebra and super algebra. Sir, I have one doubt. How can you, sir, correlate cluster algebra and unimodular row?
So, you see this, which I told you, AD minus this is a. So what I'm saying here is that
Yes, sir.
you have this, right?
Mm-hmm.
So if you remember, here is a very quick way to see at least one construction I can show you. So remember, I told you that if you start with 2 variables, right, and you take this quiver, right, and you do all the mutations, then you get 3 new cluster variables. Those are 1 plus x1 over x2, 1 plus x2 over x1, and 1 plus x1 plus x2 over x1 x2. And if you put them a little cleverly, I might make a mistake, so but I'll ask the young student to try. Probably they can do it better. So let's put a bunch of ones here, okay? And suppose I put 1 plus x1 over x2 here, x2 here. So if I multiply this, will be 1 plus x1. So if I put x1 here, so you see this will satisfy the unimodular rule, right? 1 plus x1 over x2 multiplied to x2 will be 1 plus x1, minus x1 will be 1, right?
Yes, yes.
If you put okay, so you can play with these things. So maybe so if I put this will be product will be 1 plus x1 plus x2 by divided by x1. So if I put, will this work? Probably not. This will be, so this product is 1 plus x1 plus x2 by over x1 minus 1 plus x2 over x1. So that's x1, right? Yes. Let's check if we can do college algebra. So this x2 cancels, this 1 cancels. x1 over x1 is 1, right?
Yes,
So
sir.
now you can see, you can put all those things. Also, those of you who are familiar with Ferri fractions, it relates to Ferri fractions also. You know Ferri fractions that you take this and then do the dream addition of kindergarten as such. So in between you put a plus c over b plus d, right? So if you do that, you get a series of numbers, which is called Serre series of Serre fractions, and they also can be put into any Fritz pattern, and so it goes to cluster algebra. So did I answer your question?
Yes, sir. Thank you, sir. So from participants, if you have any doubts or any query, please you unmute your mic and you can ask to sir. I think one participant, Rasid, no, who is the Rasid Ali? Your doubt is clear, or you want more clarification? So you may ask your question to sir. Okay, okay. Actually, he has written, but I think, okay, he has no doubt. So, okay, thank you, sir. Thanks for your such an enlightened talk. Thank you very
Okay.
much, sir. And
Okay.
especially in the late night in the USA. Thank you very much, sir.
Thank you. Thank you.
Gupta,
All right.
sir, you want to say anything to sir?
Thank you, sir. Yes, now we will meet again at 10:30
Okay.
for
All
the
right.
next lecture.
Okay.
Thank you
All
very
right.
much, sir, for this lecture.
Okay, sir. Bye.
Bye.
Okay, everyone.